Good afternoon, everyone. I see that everybody's back and hopefully all set for a great afternoon session. All right, my name is Nishith Nedungadi and I have
Kiran, Kasichayanula.
We are from Bloomberg and we are SREs in the Feeds Engineering Department. Our team focuses on reliability of the feed handlers and the environment in which these feed handlers run in. That's what our primary focus is. And today's talk is going to be about the challenges of managing real-time market data storage. So, the way we have So the way we have structured our flow today, I'll be setting out the context of market data by introducing it, why it's important, what are the various use cases. I'll also take a deep dive into the nuances and challenges of the environment that these feed handlers are running on. It's a global scale environment across the world, and how do we manage the market data storage across such a wide platform. Subsequent to that, I'll hand it over to Kiran, who will take a deep dive into a solution to handle the challenges of the storage. And from there, we'll talk about some of the future steps that we'll be focusing on. Okay. So most of you might have already been aware of Bloomberg, more in terms of what it does. To give you just a super brief introduction, Bloomberg main product is the Bloomberg terminal, and the terminal delivers a wide array of information to our clients. This information includes real-time market data, real-time news, analytics, on which our clients make financial decisions. Our clients include the entire financial market, like the hedge funds, investment banks, government agencies, regulatory agencies. We also cater to both individual and enterprise workflows using the terminal product. A big part of the data that we have in front of us is what we publish to our clients is real-time market data. What exactly is real-time market data? In finance, price and other related information associated with a stock like Apple or IBM, and which is published by trading venues like stock exchange, is called as market data. That's really what market data is all about. Information about any financial instruments, not necessarily limited to stocks. It could be things like options, it could be exchange conversion rates, currency conversion rates, and so on and so forth. To further put flavor on what market data is about, let me take you through a simplified workflow of what a trader would do. So let's say the trader wants to buy or sell a particular stock. For that, the trader enters a particular order. There are different types of orders, but it could be information about this order is disseminated and published by the exchanges. And that's what kind of shows up in the order book that you can see highlighted on the screen. Once the trader has put in, or traders have put in their buy and sell orders, the best of the buy and sell order is also disseminated by the exchanges. That's called as quotes. Subsequent to these dissemination, the magical matching engine of an exchange matches the orders and we generate a trade. The trades and information about trades, the prices, the size, all of that is also disseminated by the exchange. So in effect, the security, orders associated with the security, quotes associated with the security, trades associated with the security, information of all of these ideas are what is called as market data. And market data is extremely important. It's used for price discovery. It is used by the trading algorithms to trade. It's used to determine liquidity in the market. It adds a lot of observability in the market. That is why market data is extremely important, and real-time market data is even more important based on which people do their trading. So that's essentially the kind of context of market data. In addition to this context, I'd like to add one more context. It's all about normalization. The way exchanges send information as basic as trade price and trade quantity can differ. Let's take the example of the one on the top. The price and quantity have been disseminated in a much more verbose fashion. And that's part of what the exchange wants. In the second example, the same price and size by a different exchange is disseminated in a binary format. That's essentially the need of the market. It might be optimized for high throughput and low latency. So the main takeaway here is exchange don't send market data on a whim, they send it for their business context. Obviously, the challenge is if you were an application writer, you really don't want to code against these different data formats, coming over different data protocols, and so on and so forth. You want something to normalize it. And normalization is where an example normalized market data is what's shown on the screen, where we take something like a tag like market data entry price, change it to a trade price, and change a tag like market data entry size to trade size. So normalizations like this allow us to abstract the variations out of the downstream applications that will consume this data and can just focus on how to process and maybe focus on their functionality. That's what is called as normalization. So now that we've discussed market data, some characteristics of market data, the variations that exchanges send this data in, we discussed about normalization. Let's take a further, continue our journey into how is market data processed in the Bloomberg pipeline. Just an example of that. All right, so once the exchange sends the market data, the feed handlers applications consume this data. They have two jobs, connectivity and normalization. They connect to the exchange, establish resiliency aspects, and then they normalize the market data. This normalized market data is then sent downstream to a storage, to storage, and from storage it's disseminated to the data distribution infrastructure. Using the unified interface of our data distribution infrastructure, the terminal and the clients from our terminal and other enterprise application consume this market data. Our talk this afternoon is going to focus on the feed handler segment of this pipeline. Let's take a deeper dive into that segment. That's a feed handler. It, as I mentioned, has got two primary reasons. One, establish a session. Two, normalize. The main objective of this feed handler is to process market data as fast as possible and send it downstream. That's all it cares about. High throughput, low latency, and that's all it's optimized for. It does generate two data files, the raw market data file and the normalized market data file. And these data files are very important, and we'll discuss this in the next slide. But this is the focus of this presentation. How do we manage the thousands of market data files that we generate, and how do we, again, manage the storage associated with them? So, why is it even important to manage this data? What's the big deal about it? We use these data for various reasons. One of the things that you have to understand is for a feed handler, all data that is disseminated has to be journaled. We journal this data for debugging purposes. We journal this data to answer client queries. We journal this data to understand the events that took shape in the market. That's essentially the primary reason that business uses these data files. As I mentioned, they answer client queries. There are queries where things are different on the terminal, and there's a question whether exchange sent it or was it our normalization that may have changed it. These are important queries which we have to answer. Business and engineering also use it as a communication tool. When new exchanges come into existence, the first thing they send out is raw data. So we use that to analyze requirements and ensure that it is normalized and parsed properly. We use the raw data file to do that. We use the developers, the engineers, they use this data to debug their output, to make sure that the normalization makes sense. Whatever they wanted is indeed part of their output. They use it to validate the correctness of their processing, and they also use this to recover from outages. As I mentioned, every data has to be journaled, has to be streamed in order, and in certain cases has to be replayed in order to recover from outages. That's the why behind why do we need to manage these data files. To continue on the same discussion, right? So we've gone through the why behind these, why is this required to manage the data files. Now let's take a look at the existing system when we started to kind of dig deep. It was a reasonable system. We had a script that would back up these data files on the local storage. We also had a variable number of backups that would be sent to the network file storage attached to these feeds machines. And we had a dev utility that would be able to download the requisite files when needed by the users like the business counterparts or engineers. Reasonable. As we dig deep into the system, I will be able to give some more color to nuances of our system, and that should kind of make some of the issues or challenges with such an approach apparent. First thing is non-uniformity. Every feed handler is unique. We discussed about how it's different type of data that it consumes and over different data formats and protocols. It's not just that. These feed handlers generate different types of files. They may have different names. They may be generating these files at different locations. They may have different number of files depending on the volume of data it processes. So you could imagine there's a lot of variation. Exposing this variation as a dev utility to our business counterparts, to our engineers, it becomes unmanageable. They would now need to know what each feed handler generates, which machine do those feed handlers run on, where do they generate these files. And notice all of these files are mostly binary files. So now they need to somehow know how to decode these files and then figure out and move on with their real functionality, right? So it becomes unmanageable when this variation is exposed to our users. The other interesting thing is capacity of market data. So the chart in front of you shows the exponential increase in market data over the last 12 years. We hit 100 billion in 2016, 200 billion in 2020, and I think last year, 300 billion messages a day. There are a couple of things that you should notice, and I'll probably come back to it. The spikiness of market data. It does increase throughout the 10 years, But there are areas and places where it seems much low. This 300 billion messages per day translates to approximately 100 terabytes in the last 24 hours. That's actually a real number. And thousands of files per machine. With such variation in market data, it becomes difficult to scale the local disk of a feed on demand. It also becomes difficult to scale network file storage on demand. There is a lot of variation in input, which usually translates to incorrect uniform backup policies. We sometimes may take the day zero or the current day data and give it more priority than backups to ensure that the machines are okay, are able to process the current day's data. That's the highest priority, right? That's what the whole feeds machines are there for, to process real-time process market data. So this becomes an issue because we are unable to scale and scale fast. We are unable to have a uniform policy that's applied. That's the issue with capacity. The other thing is the environment or feeds environment in Bloomberg is global scale. We handle market data from 650 different exchanges across the globe. So we have our machines spread across the globe in various data centers across various network zones, allowing access to these network zones and allowing users to download market data during maybe active market hours can constitute a bandwidth issue. So that was other issue that we realized that in certain cases we could be impacting the processing of market data or the available bandwidth of market data. We also realized that this could be considered a security concern. Albeit it's within the Bloomberg network, we definitely wanted to make sure that we consider security as a primary, as a first-class primary aspect of the new system that we wanted to build. So network zone securities and bandwidth was a concern. As I'm talking a lot about files and data files and storage, there might be a question on why files? After all, we are in 2024, maybe we should, or 2023, sorry, maybe we should be discussing about streaming, right? So the idea of files is a couple of things. There were at least two interesting the points there. One is existing interface. We have thousands of instances, tens of thousands of instances of feed handler spread across hundreds of machines. The idea is to not go and change the interfaces. Today, the file as an interface existed. Every feed was generating the raw and normalized data file. Our job was not to go and change the interface of that file. That was number one. Number two, again, goes back to the characteristic of market data. I showed the market data across 12 years, few slides back. This is across 24 hours, and you can see the same spikiness in this market data. The feed handler is optimized to handle the spikiness. It's optimized to handle this load with high throughput and low latency. What it's not optimized is to back up this data. The files allows it to decouple itself from any other sidecar application that could take this data and back it up. It is a natural buffer between the publisher of market data, which is what its primary goal is, and the backing up and archival of market data, which could be the goal of some other application on that particular machine. So it gives you a good buffer to do that. That's the second reason we persisted with files, but it can change in the future. All right, so coming back to the requirement. It's familiar, right? Business analysts and engineering need a system to access the incoming raw and the normalized market data. But I'm hoping that there's been a lot of color added to this particular requirement and to the challenges that we face in a global platform. We definitely want it to be scalable. Whatever solution we come up with has to be scalable. If we had just 1 or 2 feed handlers, it would have been easy to customize it. But the fact that we have thousands of instances of the feed handler makes us introduce or makes us okay to invest in a different type of solution that takes these characteristics up front. We need to manage scale, it has to be agile, and it has to be a system that can manage this variation and allow a uniform policy to be put forward to our users. With that said, I'd like to hand over to Kiran, who will take us through a deep dive into the architecture of a solution that we have.
Thank you, Nishith. So, moving on. What we want is a solution that's highly scalable, easily accessible from all our feed handlers across the globe, has a uniform storage policy, as well as maintainable. The nature of the market data is such that these variations are very common. We cannot predict the market data, spikiness, or the growth. The way we have structured and designed this storage is, it's a private cloud, but with S3 access patterns to make sure that it's universally accessible, which means that the storage is Bloomberg's, but the access patterns are S3, and we use Boto3 library to access it. A file is stored on the cloud using object storage. We have discussed file storage versus object storage, and since the files themselves are binary files, we thought object storage is a preferable method to store these files. The next part was to take the file properties and embed them into the file object itself to make sure that we are able to recreate parts of or complete picture or complete file with these paths. This can be used for analytics. We can understand how many paths have been uploaded for a given file, or how many files do we need to reconstruct to create the complete file. Another challenge before us is the network zones. Yes. Oh yeah. Don't know. Okay, whatever. So we have multiple network zones, obviously, for security reasons, and the reason for that is we have DMZ, demilitarized network zones, which we have to expose to various exchanges around the world, and they connect to our machines to send us data. That set of machines need to be separate from our production environment, and this causes various issues for us. For example, if a user wants to get data from those machines, obviously we need to open a tunnel and from our dev machines onto the DMZ, as well as uniform access policies are violated in that DMZ zone. They might have special network requirements. So to handle that, we have open proxies for all the network zones which are dedicated to this cloud infrastructure and would send the data appropriately. Now that we have established cloud as a storage, we need to push data from hundreds and thousands of our feed handler machines to the cloud. That's where our agent infrastructure comes into picture. let's take a deep dive into this agent and what are the constraints that go along with the agent. As explained by Nishith, the primary job of the feed handler is basically to process market data. Market data is spiky as well as is very vast. We cannot lose market data. So the primary job of this feed handler machine is to process market data. And we are just a sidecar application which take this normalized and raw files and store it in a cloud storage. One of the properties one of the things that we have used to make this sidecar application adhere to the constraints of feed handler machine is async.io. But before going there, let's take a deep dive into the agent itself. The primary job of the agent is to find files, is to read the files, chunk the files, and upload those chunks. This is where the event loop concept of async.io comes into picture. Event loop helps us read and process multiple files at once without writing the parallel code. Let's say a thread is waiting on probably fetching new data. It can process it can process something else like reading files which can be assigned to that thread. And this is where async.io comes into picture. As explained, the primary job of the local agent is to read the file, chunk the file, and upload the file. But agent also needs to support custom files. We have feed handlers which produce different files at different locations, and we support the custom configurations which feed handlers applications can add on to our agent so that we will start monitoring those files. We have built two kinds of rate limiters onto the agent architecture because we wanted to be efficient about two kinds of resources, disk as well as memory and I/O. Let's take a deep dive into the disk rate limiters. The disk rate limiter enables us to limit the amount of disk usage that we have on the feed handler. Let's say these hundreds of files are produced, but if we start observing and chunking these hundreds of files, we might be overutilizing the amount of disk I/O that's available on the feed handler. But the feed handler machine's primary job is to process the feed handler. So we have a limit on this disk I/O. The pipe size of this disk rate limiter is 30 GB. And we can process 32 MB chunks at a time. So in essence, we will be processing 1000 chunks. They might be from the same file or they might be from different files. Another interesting characteristic of this agent is the network rate limiters. Once these chunks are produced, we need to get these chunks into the cloud, and that's where this network rate limiter comes into picture. We have to optimize for the network bandwidth as we have to make sure that there's enough bandwidth for the feed handlers to process market data, and they have to send it to a database. So once these chunks are produced, those chunks are compressed, and we use zlib compression, and approximately we get like 4 MB chunks, and we pass it through a global rate limiter. The global rate limiter we are using is a Reddish cache, where we have defined a block as 100 MB for every 5 seconds, meaning that if agents across multiple feed handlers ask for more than the 100 MB for every 5 seconds, then then it will be divided amongst n number of agents. So in essence, if 10 agents ask for this network resource, then it is going to be divided. We do that to make sure that again optimizing for the global network resource. As well as another rate limiter that we have built onto this agent is a local rate limiter. The size of the local rate limiter is 20 MB per second. Once it passes through the global rate limiter, then we pass the number of chunks through the local rate limiter, and if those chunks are within the capacity constraints that we have defined, they end up in the cloud. Notice that the market data itself is spiky. So over a course of 24 hours, this data will eventually end up where it's supposed to go. The feed handlers themselves, which are on the feed handler machines, are optimized to process market data. One of the optimizations they use is memory mapped files. And by doing that, what they do is they pre-allocate 2 GB or n GB memory mapped file in the OS namespace and write whatever they need to write. For example, they might be writing only 100 MB chunks, 100 MB chunks to that particular file. So 100 MB chunks, but the rest of the file will be garbage. If an agent is not aware of this property of the feed handler, it would read and process the chunk, and not only the chunk but also the junk data would end up in the cloud. There would be reconciliation at the end, but it would still be using this network and disk I/O inappropriately, which is not a desired thing that we would like. So our agent, which sits on the feed handler machine, is aware of this property. So what it does is it goes and reads a particular memory location which the feed handler has written. So feed handler writes to a memory location saying, I have only used 100 MB of the data, so go to the file and only read 100 MB. So this optimizes for the disk. Another intrinsic property of our agent is the way it handles these data files. Market data conditions are such that they vary too much based on what the exchange wants to do. Some exchanges are open 24/7, some exchanges are open 7 days, and there is no downtime. There might be a downtime of 1 or 2 minutes, but that's besides the point. The point here is there's so much variation that we need to provide a unified interface for our users, irrespective of the market conditions. just so we have designed the agent in such a way that we keep track of when the market opens and when the market turns, when the market closes, and when the file turns. Just by that, if a user of our application would like to get the information for the session, he would be, or she would be, or they would be able to get the information just by knowing when the market opens. We have spoken a lot about how we send the data and how we store the data. The next part is more about how we use this data. Who are our clients, right? We have three kinds of clients based on their use case. As explained by Nishith, there might be a developer who would like to verify, am I processing the correct information? Are there bugs in it? Maybe he wants to replay an anomaly. There might be a business user who wants to make sure that the requirements are met. Maybe fine-tune the requirements even better. Or maybe they want to talk to the exchange and make sure that the data that's being sent is processed accordingly. There might be an analyst who would like to take this data and put it into big data and try to run analytics, right? Why did it happen? We get asked that, we get those kind of questions quite a lot. So, to satisfy our clients, we have to provide the same data using multiple interfaces. But it has to adhere to our conditions that are defined here. They want intraday data. They want data as soon as possible. They want on-demand access. And they want to test and play with the data whenever they are able to. We have to monitor our own application the same way feed handlers monitor their applications to make sure we are meeting our SLAs. Our SLA for our application is 2 hours. Notice that we are a sidecar application, which means our SLA of 2 hours is more than fine. It's perfectly okay because the primary job of the feed handler is to process market data. As you can see, we are under a minute. So bringing it all together, we have cloud infrastructure in the middle, feed handlers and feed handler agents on the left, and the clients on the right. Notice that there is no overlap. This is by design. The network as well as the disk on the feed machines are very valuable resources. So, if a client of that data would be using those resources, it would be hard for us to push the market data downstream. Of course, the work is never done, right? The market data, as you have noticed, is scaling from 200 billion messages to 300 billion messages. God knows it can go to 100,000 billion. So we have to scale our application to make sure that it's taken care of. Users cannot be left in the dark just because the market conditions have changed. We have some work on in front of us with respect to the way we are storing objects. We are totally fine for now, but there is a limit on the number of objects that goes into a bucket, which means that we have to optimize and increase and redesign probably how we are storing objects in a bucket. But it has to be done seamlessly. There cannot be interruption while we are redesigning this object store. Also notice that we have the upload times for a chunk is around 40 seconds, which is still okay, which is still near real time, but we would like to move it to real time. Clients, internal clients also are as demanding as our external clients, and we would like to make sure that they are happy. And for that, we need to improve observability, both on the server side as well as on the client side. So to summarize, here are the takeaways. We have shown the characteristics of market data and how we manage the market data. And by applying cloud to market data, how can we form a solution? Now, given that it's a solution, right, there are improvements that can be made to this application. And what are the considerations that went into building this system? We have shown that we have rate limiters that are built into the agent. We have shown how we have designed the object store. We have shown how we are processing session information. So those were the takeaways that I hope you have you have taken away from our talk.